So we're going to look at another kind of comparison test. This is called the limit comparison test. This will be used when you have a series that resembles a p-series or some other well-known series like geometric, but you can't establish a term-by-term comparison. So we'll be using what's called the limit comparison test. So let's look at a couple of examples. In this first example, we actually can use direct comparison, but I'm going to show you how the limit comparison test works. Notice that if we choose to compare this series to the series square root of n over n squared, again under the same idea as the direct comparison test, remove sort of all the non-essential terms, this is the p-series 1 over n to the 3 halves, which is a convergent p-series. Now adding 1 in the denominator makes the entire term smaller. So these terms are all smaller than a convergent p-series, so we can also say it converges. But we're going to instead try this new test. So let's first note, let's just evaluate the following. So you may not understand why, but just sort of follow me for a moment. We are looking at the limit as, look at the limit as n goes to infinity of their ratio of these two series. So let's just go ahead and do this computation. I'm going to pause it and do the computation out. So we get the limit of a sub n over b sub n. Note that now I can flip and multiply my ratios, which I'm going to again do unpaused. So flipping and multiplying, we have this expression here. This is of course the same thing as n to the 1/2. So we multiply with this we multiply powers with the same base. We add the exponents. So we get n squared over n squared plus 1. This limit, since the polynomial, this is a rational equation with rational expression with the numerator and the denominator at the same degree. This is going to go to the ratio of their leading coefficients, so it's going to go to 1. So now we're asked some questions about this expression. They asked us, so the fact that the result above is 1, what does this mean for the limit to approach a number? So what we're saying here is that the ratio is constant. So in some sense, they both behave similarly. As n approaches infinity. Okay, now would it matter which series was in the numerator versus the denominator? Well, no. If you're getting some limit, some constant limit, then you know that they're both behaving similarly, whether it's 1/3 or 3. If you think about taking a convergent series and multiplying it by any constant factor, a 3 or a 1/3, it's still going to stay convergent. So it doesn't matter which was in the numerator and which was in the denominator. If we know that the limit is approaching some constant, we know they both are behaving similarly. Likewise, if the limit were to approach 0, that still would tell us that, if anything actually, that would tell us that the numerator was smaller than the denominator, and that would still tell us that our series converges as well. In the second example, we have a case where direct comparison wouldn't work. If we again removed all the non-essential terms, we'd be comparing to 2 to the n over n squared. And it's not really, that would be still comparing to a divergent series. In this case, it's not because it's a p-series or geometric, but if you did the nth term test, so take the limit as n goes to infinity of 2 to the n over n squared, and you won't get 0. So we know that series diverges. So again, let's look at the limit of the ratio. Again, for time's sake, I'm going to pause it and just do the computation. So we see that this limit equals 1/4. Again, you should take the time to make sure you understand this computation. So again, we see that the ratio equaled some constant. Ratio equaled 1/4. So this is again telling us that our series behaves similarly. So this would tell us that both series diverge. Again, it wouldn't matter which series was in the numerator or the denominator. A constant multiple times something convergent or divergent is still going to remain convergent or divergent. So it doesn't matter which one is in the numerator versus denominator. So it doesn't matter that the ratio went to 1/4 or 4, is what I'm saying there. And what would happen if this limit approached infinity? That would just be telling us that our series was infinitely larger than a divergent series, so this would still tell us that both diverge. Okay, so I wrote some notes there when it was paused to make sure you understand what I just wrote there. So our limit comparison summarized is that if you take the limit as n goes to infinity of the ratio of your original series with the one that you're comparing it to, again, the thing you're comparing to should always be very similar, except you just remove sort of the non-essential terms. If you get some limit, and that limit is greater than 0, then whatever your comparison series does, so will the one that you're trying to evaluate. So they either both will converge or both diverge. So if you picked a divergent series to compare it to and you get some limit, then your original will diverge. If you compared it to a convergent, your original will converge. In the case of 0 infinity, it depends on whether your original series converges, your comparison converges or diverges. So the first example we looked at today, the thing you're comparing to converged. So if your numerator is so small that you get a limit of 0, your series is significantly smaller than a convergent series and so must also converge. In the case that you're comparing to something divergent, if your numerator is so significantly larger than a divergent series that the limit goes to infinity, then clearly both of them will have to diverge. And a note here that the limit comparison test is especially useful for series in which a sub n is a rational function of n. That's because you're going to be looking at a limit of a ratio of two rational functions. Notice in both examples we did above, we were sort of doing this flipping and multiplying, lots of things canceled out, and in that case it will be easy to actually evaluate the limit. So we're going to do some examples now, but being mindful of time, because I know the last video was a little bit too long, I'm going to pause it and do some of the work while you're not watching. If you can't follow it at this speed, then obviously pause and make sure you can follow everything. So let's look at the first series in part A. Take a moment and think about what you would compare this to. So I would compare it to this p series 1 over n squared. If you said 1/3 and 1 over n squared, that's also fine because you could of course pull out that 1/3. Now, is this a convergent or a divergent series? Again, ask yourself, and the answer is that it's a convergent p series. Now let's set up the limit. So this is the limit of our original series to the thing we're comparing it to. I'm going to simplify and evaluate off screen. And we see that we get 1/3. This is a limit. Doesn't matter how big of a limit it is, it's just a limit. That tells us that our two series behave very similarly as n goes to infinity. So that tells us that since we compared to a convergent, our original will also converge. Okay, let's look at another example. Again, ask yourself what you should compare this to. We can compare this to 1 over square root of n. Again, if you had the 3 in there, that's okay, because you in a sense could just factor that out. And what kind of series is this? It's a divergent p series since p is a half. So again, let's set up the limit. So I know that's a little bit crowded there, but there's the work. Again, pause the screen if you must to follow it. So we get the limit of the square root of n over 3n minus 2. In here, we know that this ratio goes to 1/3, so this whole thing goes to the square root of 1/3. Now that is a constant. It's not a pretty constant, but it's a constant nonetheless. So since our original series diverges, and our series behaves similarly enough that they just differ by a constant, then we know that our series diverges too. Okay, trying to be mindful of time, I'm going to again write a lot of this while you're not watching. So pause it and maybe try this problem on your own and see if you can get the same thing that I get. So we compare to the convergent p series 1 over n cubed. Remember when you're evaluating this limit that you do have to distribute the n cubed in the numerator. So we get a limit of 1/4. And so our series also converges by limit comparison test. Okay, try this next one on your own and again compare. So we compare to the divergent p series 1 over n. And this limit equals 1. So since we compare to a divergent series, our series also diverges. So for all of these comparison problems, when you're doing these on a test, for example, or homework, I'd be looking for you to tell me what you're comparing to, whether the series you compared it to diverges or converges. I'd be looking for the work that demonstrates the test, and then the conclusion that you get based on the results. Okay, there are 2 more examples. I'm again going to do these out. I would recommend that you pause the video and try them on your own as well. So we see that this series converges. Okay, try this next one. Note with this comparison, n times the square root of n squared is just n times n, so we're comparing to the convergent p series 1 over n squared, and this limit equals 1. If you had a hard time seeing that, remember that if you're looking at this denominator, as n goes to infinity, this 1 plays a very little role, so this is again like n times n. So again, our series converges. As always, the limit comparison test will not always work though, so note that there are only certain cases that apply. So we have, if we get a limit L, then that tells us something. If we get 0 and we're comparing to a convergent series, that's telling us something. Or if we get infinity and we're comparing to a divergent series, that tells us something. But what would happen if we get a limit that goes to infinity, but we were comparing to a convergent series, right? If b sub n converged. So in that case, we don't know what happens. The limit comparison test is inconclusive in that scenario. And likewise, if the limit goes to 0 and we were comparing to a divergent series, that is also inconclusive. So make sure you make note of what I just said here.